Hi, my name's Dyke, and my primary role is team management.
Hi, I'm Chris Rathman. My primary role is rocket design and analysis.
Hi, I'm Kevin Ong, and my primary role is CAD.
Hi, I'm Kyle Troyer. My primary role is drone structures and control.
My name is Madison Reints, and my primary role is manufacturing.
Hi, I'm Trey VanVelsor. My primary role is drone avionics and piloting.
The goal of the SISYPHUS is to land a vehicle carrying a golf ball payload to the target area as accurately as possible. The SISYPHUS system will consist of three components: the SISYPHUS rocket, the Hubris release mechanism, and the Boulder delivery vehicle.
Following this year's updated competition rules, SISYPHUS is a two-stage rocket. Fully stacked, the rocket will be 10 feet tall with a pad weight of roughly 35 pounds using 4-inch tubes. SISYPHUS is a custom design using Wildman rocketry components. Using an L-class motor in the booster and a K-class motor in the sustainer, we will be able to comfortably deploy our return vehicle above the 9,000-foot threshold. All rocket avionics are Altus Metrum products. In the booster, we are using a Telemetrum and redundant Easy Mini. This will deploy drogue at booster apogee and fire a cable cutter at a booster main deployment of 1,250 feet. In the sustainer, we are using a Telemega and a redundant Easy Mini. This will fire a stage separation charge, sustainer ignition, a drogue/return vehicle deployment at apogee charge, and a main deployment at 1,250 feet. The highly unique Boulder Release Initiation System, or Hubris, has been specially designed with comfort in mind for our drone. The objective of Hubris's design is to provide a deployment system that does not rely on mechanical processes to prevent the possibility of mechanical failure during deployment. Hubris consists of a plunger built out of a coupler tube with fiberglass bulk plates fitted inside. A carbon fiber rod will run through the plunger and into the body cavity of the rocket. The boulder, with mounts attached to the underside of the base plate, will slide onto the carbon fiber rod. Separate foam placements on the sides of the motor arms will stabilize and cushion the drone during ascent. At apogee, when the drogue parachute is released, it will pull out the plunger and foam inserts and push our drone out of the body tube. The rotational force of the Hubris system, along with slight gravitational interference, will allow for the boulder to slide off the Hubris system and into free fall, where it will stay until arming at around 2,500 feet above ground level.
The chosen delivery vehicle, the Boulder, is a tricopter running a Kakute H7 mini flight computer. It consists of two front motors extending forward of the frame, separated at a 120-degree angle. Mounting and compacting the arms forward of the frame, instead of within the bounds of the frame, allow for a shorter body length and increased structural integrity. A shorter frame will also reduce the effect of twisting the body frame when rolling and bending with pitch. The third motor is mounted aft of the base plate. The aft motor is gimbaled by a servo mounted in front of it. Gimbaling the aft motor produces varying directions of thrust, allowing the delivery vehicle to yaw. Fitting the delivery vehicle into the rocket was one of the main design challenges, and the tricopter design allowed an easier fit with less risk of deployment issues, such as arm damage or skewed deployment. The front arms are outfitted with torsion springs, allowing them to be compacted to fit within the 4-inch diameter rocket tube, but the rear arm was designed such that it will fit longitudinally into the rocket without needing to worry about compacting an additional pair of arms. The Boulder, in its pre-flight state, with arms compacted, is 18 inches long, 3.1 inches wide, and 3.5 inches tall. It weighs just over 2 pounds. At apogee, the drone will be released from the rocket, extend its arms, and fall to approximately 2,500 feet AGL, where it will arm. The Boulder is intended for autonomous flight to the target, but it also includes an FPV camera in the case that manual control at the target location is decided.
To allow for rapid prototyping, many of the initial parts for the wooden iteration of the Boulder were 3D printed out of PLA filament. These pieces went through many different iterations to allow for stronger designs, built-in wire management, and helping to determine what non-3D printed parts needed to be improved upon. For the competition versions of the Boulder, all of these pieces will be 3D printed out of onyx filament to improve overall strength for the rocket launch.